So let's now have a look and see how these symmetric and antisymmetric normal modes interact using Mathematica. We'll start here with some initial conditions where both the masses are at rest, but they're displaced. One of them is displaced by positive 1 and the other one's displaced by negative 1. They're the initial conditions. And when we let them go, they oscillate in antiphase. So the amplitude of the motions is equal, but they're oscillating out of phase with each other. This is just exciting the antisymmetric mode. The symmetric mode has not been excited at all. You can see its amplitude here is 0. If we now start with the symmetric condition, so both masses are displaced equally by 1 unit, then we see the motion of the masses is identical, it's overlapping, and this is just the symmetric mode excited. And you can see here also the frequency is a little lower than the antisymmetric mode. So this is the case where the spring between the masses is doing no work at all, and the distance between the masses stays constant for the duration of the motion. If we now have a situation where we displace only one mass, then we have this situation that we first saw when we were looking at coupled harmonic motion, where we displaced the blue mass and then let it go, and you could see it oscillate, oscillations decay, and it gave its energy to the red mass. So now what we're seeing actually is the beating between the symmetric and antisymmetric modes, because now we've excited equal amounts of antisymmetric and symmetric mode. They have different frequencies, and so we can see here the beating between these two different modes. The phase in this case, the phase of both modes is 0. If we look now at some other sort of arbitrarily chosen initial conditions, where I give it some initial velocity, some different initial positions. So here's a situation where we don't completely exchange the energy between the two masses. We have different amplitudes in the symmetric and antisymmetric mode and different phases. So in this way, we can build up a complete ensemble of solutions for all of these initial conditions using particular phases and amplitudes of the symmetric and antisymmetric modes. Let's have a quick look now at the effect of the spring that connects the two masses. It is this spring that allows energy to move from one mass to the other. It's a spring that couples the two oscillators. So if we move this spring constant, K1, down to 0, these masses, the blue mass and the red mass, are no longer coupled, so when we excite the blue mass, it oscillates without giving any energy to the red mass. If we increase K1, so we introduce some coupling, now we can transfer energy from the motion of the blue mass to the motion of the red mass. If we look at these two curves of the red and the blue in isolation, what we see is something that looks like a beat. Well, this beat frequency here is the beating between the two normal modes. When we just excite the blue mass, what we're doing is setting up a superposition between the two normal modes, and so the normal modes beat with each other, they have different frequencies, and so we see this beating. By increasing the spring constant, we increase the rate at which energy can move between the two masses, and we increase the frequency difference between the normal modes, and so we see a higher and higher beat frequency as we increase the spring constant K1. So here's an example of a fiber optic coupler. We put light into this fiber on the top here, and it can travel through this fiber and come out, but it's very close to another fiber at the bottom, so close in fact that light can couple and travel between the two fibers. And so you see, when you put all the power into the top fiber, which we call the primary, it leaks out into the bottom fiber, so the green one here, the secondary fiber, is excited and goes back and forth. The spacing between these peaks, the coupling length, depends on the distance between the fibers. If I make the fibers closer together, the coupling is stronger, just like increasing the spring K1, and the distance between these peaks gets shorter. And this shows you the field amplitudes as you go from each of the peaks in this coupling length. What about a really exotic example? What about something from quantum mechanics? So let's imagine we have an electron that's trapped in a potential well. So this is a square well potential, and there's an electron trapped in this well, and this is the wave function of the electron here that represents the probability of the electron being in this well. Close by is a second well, and there's a barrier. Now, one of the things in quantum mechanics is that particles can tunnel through barriers. So when you run the simulation, what you find is that these two wells are actually coupled together, and the electron can slosh from one well to the other, just like energy sloshing from one mass to another. It's exactly the same sort of physics. If we make the wells closer together, then the energy sloshes backwards and forwards faster because we've increased the coupling rate. Where are the normal modes? Well, the normal modes are these two energy levels here. So you can see this yellow curve that pops up here, that's the symmetric normal mode. There's the antisymmetric normal mode. You can see the antisymmetric normal mode has higher energy than the symmetric normal mode, just as the case for the masses and springs.